In this section, we are going to learn about the Taylor and Maclaurin series. Okay, so what is a Taylor series? So I can tell you this. A Taylor series is a form of power series. So a Taylor series is a form of power series. But note, every power series is not a Taylor series, okay? So every power series is not a Taylor series. Okay, so let's just start for a moment with a regular power series. So we had a power series and that was the summation n equals 0 to infinity of an times x minus a to the n. Okay, actually we use cn just to make sure we didn't have a, and this is a power, so this is a power series about x equal to some number a. Okay, so we looked at some things. So for example, we had sum n equals 0 to infinity of n factorial over 2 to the n times x minus 3 to the n. That's a power series. Okay, that right there is a power series about x equals 3. And its Cn is n factorial over 2 to the n. Okay. All right. So now we want to talk about a specific type of series, power series. It's called a Taylor series. And a Taylor series approximates a function f of x. Okay, so a Taylor series is the series approximation of a differentiable function f of x. Okay, and so we require f to have numerous derivatives in order for this to work. Okay, so the power series as such is the Taylor series. So given a function f of x, its Taylor series is the sum n equals 0 to infinity of the nth derivative at some point a times x minus a all over n factorial. So for this power series, the Cn looks like the nth derivative of the function evaluated at the point a over n factorial. Okay. So one other definition, a Maclaurin series is a Taylor series about x equal to 0. So in this case, my a is 0. So a Maclaurin series for a function f of x is the sum n equals 0 to infinity, the nth derivative evaluated at 0 over n factorial times x to the n. Okay, so the only difference between the Taylor series and the Maclaurin series is the Maclaurin series is about x equal to 0, where that a is 0. Okay, so it's some of these are easy to find and some are not. So let's derive the first one. So the first one is the easiest one ever to derive, and that is the Maclaurin series about the Maclaurin series for the function e to the x. Okay. So f of x is e to the x. All right. So I like to make a table. All right. So first row. Okay. So this is going to be n. This is the nth derivative of the function. And then this is the nth derivative of the function evaluated at x equal to 0. Okay, so we're going to start off with n equals 0. Okay, so if n is equal to 0, then the 0th derivative, meaning I'm not taking a derivative of the function, is just going to be e to the x. And when I evaluate e to the x at 0, I get e to the 0, which is 1. When n is 1, I'm going to get the first derivative. Well, that is e to the x. And when I evaluate e to the x at x equal to 0, I get 1. When x is 2, when n is 2, I take the second derivative. Well, I get e to the x. And when I evaluate that at 0, I get 1. When n is 3, I get the third derivative. Well, that's going to give me e to the x. And when I evaluate that, that gives me 1. So now I can see a pattern. I don't know if you can see a pattern, but I can see a pattern. So if I go down here and I get to the actual nth derivative. Okay. Okay. I get to the nth derivative, and unless there's a freak of nature, the nth derivative of this function is still going to be e to the x. And when I evaluate that at 0, I'm going to get 1. So therefore now I actually know that the nth derivative evaluated at 0 is simply just going to be 1. Okay. So the power series that we said now is a Taylor series, but because we're doing about x equals 0 is now Maclaurin series for e to the x is as follows. So e to the x is equal to the sum n equals 0 to infinity. I have to put in the nth derivative of that function, which was e to the x. I need to divide by n factorial, and then I multiply by x to the n, x minus 0 to the n. But we said this thing is just 1. So therefore, if f of x is e to the x, its Maclaurin series is the sum n equals 0 to infinity of just x to the n over n factorial. As I said to you earlier, this was the power series for the exponential. The exponential is differentiable, it's smooth, and it has no issues. And as you can see, we already showed that this particular series converges everywhere. So we showed, I think in the first lecture, this series converges for all real numbers x. Okay, and so its radius of convergence is infinity. Its interval of convergence is minus infinity to infinity. So that is by far the first and easiest series to find. Okay. Any questions about that? Okay, so now we can say that e squared is the sum n equals 1 to infinity of 2 to the n over n factorial. That's e squared, and it's going to converge. Okay, new example. One of my favorites, f of x is going to be equal to 1 over, something's wrong. Yep, that's wrong. Is 1 over x. Now we already know that this function doesn't even exist for x equals 0. So f of 0 does not exist. So therefore, we cannot do a power series about x equals 0. So this has no Maclaurin series. Okay, so this has no Maclaurin series. But I can find a Taylor series if I choose something, anything other than 0. So let's look for its Taylor series. I can choose anything I want because I just want to. So I'm going to say about x equal to 3. Okay, so therefore what I am looking for, I want to be able to write, so my goal is to write f of x equal to 1 over x as the sum n equals 0 to infinity of sum Cn times x minus 3 to the n. And because I'm doing a Taylor series, I'm going to assume that my Cn, since it's a Taylor series, I'm going to imply my Cn are going to be the nth derivative of the function evaluated at 3. So I will get 1 over x is going to be the sum n equals 0 to infinity of the nth derivative evaluated at 3 times x minus 3 to the n, still over n factorial. Okay. Now this one is a really good one because this one allows you to be able to see, do not multiply things out. Leave them as they are so you can see what the formula is. Okay, so we're going to make another chart. Okay. So the first thing in the chart was n. Okay. And then the second thing in the chart was the nth derivative. And then the next thing in the chart was to evaluate this thing at 3. Yeah. Okay. All right, so at the 0th derivative, the function is 1 over x, which I'm going to write as x to the minus 1. Okay. And its value at 3 is going to be 1/3. Okay. All righty. The next one is the first one, and its first derivative is going to be minus x to the minus 2. And then I'm going to get minus 1 over 3 squared. The next one is a 2. Its second derivative is going to be a positive 2x to the negative 3. And so when I go to evaluate this, I'm going to get 2 over 3 cubed. Okay. Third derivative is negative, but I get negative 3 times 2, x to the minus 4. And so this is going to give me a negative 3 times 2 over 3 to the 4th. Again, notice I am not multiplying anything out, because if I'm multiplying anything out, I'm going to miss it. Okay, I'm still haven't figured out the formula yet, not quite. So when I do the fourth derivative, now I'm going to get a positive 4 times 3 times 2. Okay, that's looking like a factorial to me. So now I'm going to get 4 times 3 times 2, and then, of course, times 1. We don't have to write the times 1, but this is over 3 to the 5th. So I think I got it. Does anybody see the formula yet? I'll do one more. So the 5th is going to give me minus 5 times 4 times 3 times 2 x to the minus 6. So now I'm pretty sure that this is going to be a negative 5 factorial over x to the 6th power. Oh, 3 to the 6th power. It's a 3. Okay. So I'm going to scroll down and do a dot, dot, dot. So it seems to me like if I want the nth derivative, the nth derivative is going to give me, well, let's go back. First off, I know I'm going to get n factorial. I already see it. N factorial, it's over x to the n plus 1. So I see that too. And now it looks like it's going back and forth, negative and positive. So when it's 0, it's positive, but when it's 1, it's negative. So that's looking like a minus 1 to the n. Because when n is 0, it's positive. When n is, so all the odd numbers, it's negative, and all the even numbers, it's positive. So I think that looks pretty good. Continue my line down here. And so therefore, I think that over here, I believe that this is n factorial times minus 1 to the n divided by 3 to the n plus 1. Okay, any questions? Any questions? I could not have done this if I had 120 and 20, if I had multiplied everything out. So if I had multiplied this 3 to the 6 out, I would never be able to see what the formula is. Okay, so I'm calling this thing my nth derivative evaluated at 3. Okay, so therefore I have f of x equaling 1 over x is the sum n equals 1 to infinity of the nth derivative at 3 divided by n factorial times x minus 3. Oh, yeah, to the n. So now this becomes the sum. Oh, and this is n equals 0. N equals 0 to infinity. So now I'm going to put in minus 1 to the n factorial divided by 3 to the n plus 1. But that thing gets divided by n factorial. So therefore, n factorial is in the denominator. And then I get x minus 3 to the n. So when I am done, I have the f of x equaling 1 over x, the sum n equals 0 to infinity, minus 1 to the n over 3 to the n plus 1 times x minus 3 to the n. And I could write that the sum n equals 0 to infinity of now I'm going to leave it like that. I was going to determine, we can determine where it converges actually very easily. Okay, you can determine the interval of convergence of this. So the interval of convergence, well, let's see, this is only valid on the interval of convergence. Okay, and so I can actually, so therefore, if I want to do that, I'm going to rewrite it as f of x equal to 1 over x. I'm going to write it as the sum n equals 0 to infinity. I'm going to factor out 1 over 3. And then I'm going to write the rest of it as minus x minus 3 over 3 to the n power. And so there you have it. That's pretty cool because now this is a, and this right here becomes r to the n. So therefore, this is going to converge for the absolute value of r less than 1. So it'll converge when you get the absolute value of x minus 3 over 3 is less than 1, or the absolute value of x minus 3 is less than 3. So my interval of convergence is minus 3 less than x minus 3 is less than 3. So 0 less than x is less than 6. So it only converges between 0 and 6. And then, of course, you have to check the endpoints. And I think when you check the endpoints, you actually see that that's the only place it converges. Okay. Any questions? Because the next one is more difficult. How many students do I have on here today? Oh, I have 18 students. Okay. All righty. I am so proud of you guys for hanging in to the very end of the course. We started out with 22 students. We have 18, and that is really, 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 really good. 18 that attend regularly. Okay, now here's a biggie. These last two can be somewhat difficult. I think the one I want to start off with is the sine. Nope, I want to do the cosine. Okay, so now we want to find the Maclaurin series for cosine x. All right, so we already know that we're going to get f of x equal to the cosine of x is going to be the sum n equals 0 to infinity. It's a Maclaurin series, so it's going to be the nth derivative at 0 over n factorial times x minus 0 to the n. So this is going to be my Maclaurin series. So I am going to start my chart again. And this chart needs to be, we're going to have to continue this chart because this chart needs to go on for a little bit. We can erase what we don't need. But this one is a hard one to get. Okay. So we're going to need the nth derivative, that's n. This is going to be the nth derivative of the function. And this is going to be the nth derivative of the function at x equal to 0. Okay, so as you write your chart, I want to go back a little bit and restate some of the things that I said, okay? The first thing I said was that now we want to look at Taylor series. So a Maclaurin series is a Taylor series and a Taylor series is a power series, but you can't go backwards. Okay, so we looked at the Maclaurin series because we were looking at f of x, at the nth derivative of x about x equals 0, because we could do e to the 0. But when we tried to do it for the function 1 over x, we said this has no Maclaurin series because x cannot be 0. So we just picked another number. So we could have done this about any other value. If you could be asked to find the Maclaurin series, not the Maclaurin series, but the Taylor series for 1 over x about x equals 2, and you would do the same thing. Okay. Now we want to find the Maclaurin series about x equals 0. Well, the Taylor series, which is the Maclaurin series. Okay, so let's start. Okay, so this one is rather easy when it comes to doing derivatives. Okay, so we start off with the cosine of x. Then 1, we get minus sine x. 2, we get minus cosine x. 3, we get sine x. And 4, we get cosine x. And we do it again. We have 5 is going to be minus sine x. 6 minus cosine x. 7 minus 7 is going to be sine x. And 8 is cosine x. I'm going to go one more time. Going to do 9 minus sine x. And 10 minus cosine x. 11 sine x. And 12 cosine x. And hopefully by now, we will be able to get what we think is the nth derivative. Okay, so I guess you're saying, but it keeps going back and forth between sines and cosines. So how are we going to figure this out? Well, we got to remember, first off, these are evaluated at x equal to 0. So the cosine of 0 is 1. The sine of 0 is 0. Negative cosine of 0 is -1. The sine of 0 is 0. The cosine is 1. Negative sine is 0. Negative cosine is -1. And sine is 0. Okay. Well, I kind of see a pattern here. I'm going to get 1, 0, -1, 0, 1. Okay, so I see a pattern. Okay, I don't know if I can do anything with it yet, but I definitely see a pattern. So I'm going to swing this on down. And I'm going to start looking at this as a pattern. Okay, so I can see that all the odd values are 0. Does everybody see that? So all the odd values are 0. So here, this is 0, 0, 0, 0, all the way down. Every last one of the odd values is 0. So that means in my series, my power series, I don't expect to have a x or x cubed or x to the 5th or x to the 7th. I only expect to have even numbers, okay? So the first thing I can notice as I'm going to jot down here is that there are only even numbers in the series. Only even terms in the series. So that's helpful to me. But there's another thing I notice, that even with the even numbers, it alternates back and forth between 1 and -1. So this one is 1, and down here is 1, and down here is 1, and down here is 1. So is there anything special about those? Well, let's see. I can see now, my second thing is when n is equal to 0, or 8, and 12, the Fn at 0 is equal to 1. But now I see at 2, 6, and 10, is equal to -1. Okay, so one of the things I see in that first thing, first of all the numbers are even. Okay, so if all the numbers are even, why don't I change them? So I'm going to change them to M, and M is 2 times 0, 2 times 2, 2 times 4, and 2 times 6. All right, I'm good with that. Here, M is 2 times 1, 2 times 3, and 2 times 5. So every time my N is 2 times an even number, I get 0. But every time my M is 2 times an odd number, I get 1. So let's think about this. So here's N, and it is 0, 2, 4, 6, 8, 10, and 12. And M two times 0, 2 times 1, 2 times 2. Oh, actually, let me call, yeah, 2 times 3, 2 times 4, 2 times 5, and 2 times 6. Okay. And then Fn of 0, this one was 1. This one is -1. This one is 1. This one is -1. This one is 1. This one is -1. So 1. So now this one does look like -1 to the 0 power. And this one looks like -1 to the 1 power. And this one looks like -1 squared. And this one looks like -1 cubed. And this one looks like -1 to the 4th. And this one looks like -1 to the 5th. And this one looks like -1 to the 6th. So every time, so notice, here's a 0, -1 to the 0, 1, 1, 2, 2, 3, 3. I got a pattern. That's my pattern. So now I know that my numbers are only even. I also know there are no zeros. So here's going to be my power series. So I have the cosine of x is equal to the sum n equals 0 to infinity of the nth derivative at 0 times x to the n over n factorial. But now I know I want to get rid of all the odd ones. So let's make this the sum n equal m equals 0 to infinity. So now I'm going to have the nth derivative of 2. So look, yeah, this is going to be 2m, because we only want the even ones. 2m at the 0th power times x to the 2m divided by 2m factorial. Now, why does that work? Because when m is 0, I'm going to get the 0th over the 0 factorial x to the 0. Yay. When m is 1, I'm going to get the second derivative. Notice I've thrown away all the first derivatives because we knew all the first derivatives back here. Remember, all our first derivatives gave us 0. First, third, I'm sorry, all of our odd derivatives gave us 0. So we got rid of all of them. So now we only have even ones. And for this one, I realized that it goes with the m. So if m is odd, I get -1, and if m is even, I get +1. So this then becomes the sum of m equals 0 to infinity of -1 to the n, m, x to the 2m divided by 2m factorial. And that's what I get. So that's the cosine series. The Maclaurin series for cosine. X to the 2m divided by and similarly, which I'm not going to do, the sine of x, the sum n equals 0 to infinity, -1 to the m, x. Now this one is all the odd terms, because all the even terms go to 0 in this one. Factorial. Okay. So thus far, we've done 4 power series expressions.
Could you go back up a little bit, please? I just wanted to see what.
Yes.
Okay.
Go back to
where you first wrote what m is.
Here.
Yeah. Okay. Thank you. Okay. Thank you.
Okay. Okay, so the only thing left to talk about is when this series, there are 2 things that we need to discuss, and that is the remainder theorem. And that is to be able to tell you if I approximate it with just a certain number of them. Well, actually, I'm not going to talk about that right now. Let's talk about what happens when you have a Taylor polynomial. Okay, so this is a Taylor series. So let me write these out. So we had one Taylor series. That was the sum, oh, gotta write the function. F of x equal to 1 over x was the sum, n equals 0 to infinity. Oh geez, I gotta remember it. Did it alternate? No. Okay. Brain fog. It's got x minus a to the n, but I cannot remember. I think it's just over 3 to the n plus 1. Oh yeah, minus 1 to the n. It does alternate. Okay. X minus a, 3 to the n over 3 to the n plus 1. Okay, then we had 3 Maclaurin series. The first one was f of x equaled e to the x. That was the sum, n equals 0 to infinity of x to the n over n factorial. We also had the cosine sum m equals 0 to infinity minus 1 to the m x to the 2m over 2m factorial. And then we had the sine, which is the sum m equals 0 to infinity minus 1 to the m x to the 2m plus 1 over 2m plus 1 factorial. And I'm hoping that that is what I wrote above, because for some reason I'm not remembering if that's what I wrote. Yes, I did. Okay. So now let's talk about a Taylor polynomial. So a Taylor polynomial is a polynomial of degree n, and it approximates a function f of x, which is the sum from n equals 0 to infinity of the nth derivative at some a times x minus a to the n over n factorial. And this Taylor polynomial that approximates it says only use part of it. It's the sum n equals, I'll use capital N, over n factorial. Okay, so what do I mean by a Taylor polynomial, or a polynomial that approximates a function? Okay, so say we need to find e squared. Okay. So if we just do P naught of x, which is a constant value, would say use the first term of the series, and that would be 1. So this is a constant approximation. Okay, and it is bad. It is bad. It is bad. E squared does not equal 1. We all know that. Suppose we had P1 of x. That would say take 1 plus x. Actually, let's do something even more exciting. Let's do the square root of e. Okay. So this would say the P1 of x, this is the linear approximation. Then P2 of x will be 1 plus x squared over 2 factorial. Okay, so this would be the quadratic approximation. Now, since the full series, okay, so the full series, e to the x, is the sum n equals 0 to infinity of x to the n over n factorial, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Obviously, you can see that just by taking the first term or the first and second term or the first, second, and third term, those are not the best approximations, but they are some approximations. Okay, so therefore I can use the Taylor series, which is for us the Maclaurin series, to approximate this. So if I want to find e to the x, e to the 1, so the square root of e is simply e to the 1/2. And where's my calculator? E to the 1/2, which is the square root of e. The true answer, well, I don't know how to find e on this calculator. Oh, there we go. Okay, 1.64872 and some other stuff. Okay, so that's the square, that's approximation for the square root of e. So now let's, like I said, we have the constant value. Obviously, that's going to be terrible, but let's look at the linear approximation. The linear approximation would be to take P1 of 1/2. So that's going to be 1 plus x, or 1 plus 1+1/2. And the linear approximation is 1.5. Not too bad. What's the error? Well, the error is going to be to take 1.64872, subtract 1.5, and then divide by what the true answer is, 1.64872, and then multiply that by 100. And so let's see how far off we are. Take that number, subtract 1.5 equals, that is not right. Let's do that again. So we're going to take 1.64852, subtract off 1.5 equals, and then I'm going to divide that by 1.6872, and then I'm going to multiply by 100. So I get 8%. So I get 8.8%. That's not very good, but it's not horrible. Let's look at the quadratic approximation. So that would be P2 of a half. And that says take 1 plus a half plus 1/2 squared divided by 2 factorial. Okay. So now that just means we're going to take 1.6872 and add to that 1/8. That cannot be right. Oh, because I did that wrong. I need 1 plus a half. Oof, I've got the wrong answer, guys. Can't think. 1 plus 0.5 plus 1/8. Now that's right. Okay, so that number is 1.625. Wow, that's not bad. Just by look how close that can't be right. That cannot be right. It cannot be bigger than the square root of e. All right, then I must not have done the square root of e right. Nope, that's right. Oh, it's not bigger. I'm sorry. I can't see. Okay, it's not bigger. I can't see. The error, the true value, 1.64872 minus the approximate value divided by the true value. Did anybody calculate that yet? Got 1 minute to get an answer, Dawn. Divided by multiplied by 100. I got 1.439%. So you can approximate things even though I don't know what e squared is. If I don't have a calculator and I can't figure out what e squared is, I can use a linear approximation or a quadratic approximation. And as you can see, if this doesn't really, this is not the measurements for when a building is going to fall down, but maybe I'm just trying to measure something very quickly and I need it. I can see I get a very close answer just by taking the first 3 terms of the series, which gives me a quadratic approximation. Okay, next week, we have a lot to do. So you guys have an assignment. Hang on a minute, I'm gonna stop sharing. I'm gonna stop the video.